Hey, in physics, it's Mr. Neff. Hey, here are my solutions to the projectile motion homework problems. In number 45, it says Jennifer's bowling ball was dropped from rest. Janet's bowling ball was thrown horizontally at the same time. After the balls are released, is the acceleration of Jennifer's bowling ball greater than, less than, or equal to? It's equal to, and the reason is the only difference between the two of them is the x direction, which actually is not in the direction of the acceleration and is completely independent of the y direction, the direction of the acceleration. So the one ball is just dropped from rest and it just falls straight down. The other ball is going to be thrown off to the side, and so its initial velocity is not zero, it's blah, 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 whatever that is. So it looks at first like they're super different, but they aren't. After a moment of time, this one's going to fall down to there, and this one is going to follow this parabolic path, sure, but it's going to be just as far down as the other one, and so they're at the same height. And then in another moment of time, this one's going to be farther down. I mean, it is accelerated motion. This one's going to be at the same height. And so wherever the ground is, maybe it's at the bottom of my screen, they're going to hit at the same time because everything is the same in the y direction. The initial velocity, which was 0 in the y direction for the one on the side, so my VOY is 0. My VOX is not 0, but my VOY was 0. Acceleration is 0. Acceleration is 9.8 on both sides here, and the displacement to the floor is the same too. So this question's asking about the acceleration. They do have the same acceleration. They also have the same time to the floor, same displacement, same everything, just not the same horizontal distance traveled. 46 has 3 projectiles launched with the same initial speed but with different launch angles. Rank the projectiles in order of increasing horizontal component of initial velocity. So look, they all have the same size initial velocity. It said that. So there's a vector that represents A's initial velocity. Here's a vector that represents B's initial velocity. I'm trying to draw that the same size. And here's a vector that represents C's initial velocity, like that. Now you can see that even though they all have the same size, they don't all have the same size towards the right, which is the horizontal component of the initial velocity. A is only that big. There's V initial AX. The B is this big, V initial BX, and C is the biggest, V initial CX. So we have, in terms of A, we're going to say that we're ranking them in order of increasing. So the way I said them was initial velocity A in the x direction is smaller than initial velocity B in the x direction is smaller than initial velocity C in the x direction. Then they also wanted you to indicate the time of flight. Now the time of flight is going to be more of a y direction thing. Since A is going up really steeply, then its y component is pretty big. B's y component, I'll just draw it over here, is not as big, and C's is really not as big. Since the acceleration is the same, it's always going to be 9.8. See, gravity is going to change the velocity by negative 9.8 meters per second every second. So that means that the velocity is going to come down 9.8 meters per second every second that it's in the air. So if you're not moving up very fast, it's not going to take very long to come to 0. And so the time to the top here is going to be very small because you're not moving upward very fast. So you don't have much to subtract from. Maybe, for instance, the initial velocity maybe is like, just say it's 5. So if that were the case, gravity only takes half a second to bring that to rest. Again, I just pulled that 5 out of the air. If that's 5, maybe this one's like 8. And so then the time to get to the top is maybe like 0.8 or 0.9 seconds. And then if this one was about 10, then that means this time is going to be it's going to be like 1 or a little bit more than 1. Now, it says time of flight. The whole time of flight is double what all those are. Regardless, the time of flight for C is the smallest, then B, then A. On 81, the 3 projectiles are all launched at different speeds, so they reach the same maximum height. If you just saw my last problem, I had ones that were all launched at the same speed but different angles, so they didn't get to the same height. So now, here, one thing I can say, since they're all getting to the same height, they all started off with the same initial y velocity. So each one of them, this first one had an initial y velocity. I'll say it looked like that. The second one had the same initial y velocity. The third one did too. All the same. Now, you see the difference, though. The difference is they have different horizontal distances traveled. So they're all going to be in the air for the same amount of time because they're all going up to the same height, coming down from the same height. But since C is going the farthest, that means it must be moving the fastest because in the same amount of time it went the farthest. B is moving a medium amount and C is moving the least amount. And so now if I took those vectors and I showed them to you head to tail, just kind of at an arbitrary space here so you can just see them separate from each other. The blue one is going to be like the biggest, and then the green one is going to be the middle, and the red one is the smallest, like that. And so initial speed period, that is the blue is the biggest. It's supposed to be increasing, so we'll say it's A is the smallest, and then B, and then C, like that. And then the time of flight. The time of flight is all going to be the same. It takes to go up to the same height and come back down. That must mean that since the acceleration is the same, that's why I said those initial velocities were all the same size to start. And so that means that if they had the same initial velocity, same acceleration, same displacement, they're all going to have the same time in the air. Softball is thrown from the origin of an XY coordinate system with an initial speed of 18 meters per second at an angle of 35 degrees above the horizontal. Find the X and Y positions of the softball at these times. Okay, so at 35 degrees, let's say at something like that, there's a X component, initial velocity in the X direction, which will be the original magnitude times the cosine of the angle given. And then there's a y component, VOY, and that's going to be the original magnitude times the sine of the angle given. Now, if you use your machine for this, you're going to get 10.324 meters per second, 2 sig figs. And if you use your machine for this one, you're going to get 14.745, 2 sig figs on that. Now, they want you to know, they want to know at those 4 times, where is the ball? Well, in the X direction, you're going to say that delta X equals VOXT. Technically from your formula sheet plus 1/2 AT squared, but in the X direction there's no acceleration, so it's just this first term. So I'm going to take that 14.745 meters per second and multiply by 0.5, 1.0, 1.5, and 2.0. I'm going to do that 4 different times. When I do that, I'm going to get 7.3725, 14.745, of course, 22.118, and 29.49, and all of those are in meters. Now, in the y direction, similar but with acceleration, So in the y direction, I have delta y equals VOYT plus 1/2 AT squared. Now, the initial velocity in the y direction is going to be that 10.324 t plus half of the acceleration times the time squared. And the same thing, in that t and that t, I'm going to put in 0.5, 1, 1.5, and 2. When I do that, I'm going to get, for the 0.5, 3.937 meters. For the 1, I'm going to get 5.424 meters. For 1.5, 4.461 meters. And for the 2, I'm going to get 1.048 meters. There we go. Now, to save video time, I went ahead and I made a plot of that, x versus y. So you can see this graph is the x's and versus the y's. You can see that like here's your first x at 7.3, and here's your first y, 3.9, and so there's that point, and then so on and so forth, 14, 5.4, there's that point, and so on and so forth like that. I also did put, it said that the ball was hit from the origin, so I put the origin on there too. Now what I was supposed to do is I was supposed to put a smooth curve through here, and so I'll try to do that for you now. That doesn't look good. Try to draw the other way, smooth curve. Yeah, that's pretty good. And that kind of looks like the path that the ball would really take.